The focus of the presentation is going to be what upfront work results in a successful dense medium operation. We start with looking at lithium and other minerals in pegmatites. On the x-axis down here, we have particle densities ranging from 2.4 up to 3.2. On the y-axis, we have lithium content going from 0 to 9. And if we start in the top right-hand corner, we have spodumene, which is a density of around 3.1 and a maximum lithium content of 8.03. We then have lepidolite, which has a density of about 2.86 and a maximum spodumene content of about 7.7. We have petalite, which is a density of around 2.4, 2.45. There's a maximum petalite content of 4.5. And then you also get cookite, which is around about 2.68 density and it's got less than 3% lithium. The gang minerals going from high to low are biotite with a density just over 3, micas with a density of just over 2.8, quartz and albite at 2.65, and microcline at 2.5. We look at sample selection metallurgical test work. From the initial drilling program, the geologists will generate a model of the pit or the resource. That model is based upon drill core intersections. So you have drill cores where they intersect the lithium zone. Those samples provide the source for the test work. And so we use the test work based on drill cores, which are selected to represent what's in the ore body. Next is the concept of liberation. In liberation, what we're trying to do is you're trying to obtain maximum grade or quality at maximum recovery. So in the host rock, the spodumene crystals will be bound up in a matrix with other minerals. We go to liberation, and the objective of liberation is to liberate the crystal so it can recover it and achieve a high grade and quality. Sorry, go back a step. Look at liberation and top size. We look at the top size of ore going from 0 to 25 millimeters and degree of liberation. What we find is as we decrease our top size of our ore, the degree of liberation increases. How do we get to our top size? We use stage crushing. Remember, we're crushing in the laboratory. So we have our drill core. We select a screen which has our top size. We put the drill core on there and remove the undersize. The oversize from the screen goes to the little laboratory jaw crusher. We adjust the close side setting. We take the product from the jaw crusher back onto the screen, screen out the undersize. The oversize goes back to the jaw crusher, and we reduce the close side setting in stages until all the sample goes through the screen. And then the undersize is our sample for the test work. We look at how we determine optimum top size. The top size that you're going to be looking at is a function of your crystal size. So in this picture here, we have a very big crystal. It's blessed with such big crystals and they're normally a lot finer. So in this case, we're going to look at the affecting of top size going from 25, 15, 10, 6.3 and 3.35 on liberation. Important to note that dense medium separation does not recover down to 0 and has a bottom size. And the bottom size is typically in the range of 0.5 to 1.5 millimeters. So we have top size and liberation, and then we want to produce a yield and grade as a function of top size. So what's the connection between the two? And the connection is densimetric characterization or heavy liquid separation. So what you do is you start with a low density, you add your ore, you get a float, the light stuff, and the sinks you take to your next density. That will then generate a float fraction and a sink fraction, and you repeat this process for as many density fractions as you selected, with your density increasing from left to right. Important to note, HLS represents 100% efficient separation, which we'll never achieve in an actual plant. We look at the choice of densities for densimetric characterization. Again, we've got our particle densities on the bottom axis. If we're targeting petalite, we go typically from 2.65 down to 2.35, because that covers the petalite and the minerals of interest. And if we're looking at spodumene, we typically go from 2.55 up to 3.15, because that covers the spodumene and the other minerals of interest. Look at some typical fractional results. So on the x-axis, what we've got is the results from the HLS. So we have 2.5 floats and then 2.5 to 2.6. and so on. You can see we've got 0.1 density increments, but as we get closer to the spodumene, which we're targeting, we do it in smaller increments, in 0.05 increments. The blue represents the mass in each fraction density fraction that we've analyzed, and then the orange is the yellow is the lithium content. You can see there's a lot of material between 2.6 and 2.8. Very low lithium there, so we don't have the case here where you've got both petalite and spodumene in the ore body. And then the sinks fraction is where the spodumene would result. You can see 6.9% lithium. And remember, spodumene has an 8.03% maximum, so that's a good quality product. If we look at typical cumulative results, so we've got density on the x-axis. On the y1 axis in blue, we've got recovery to sinks. And if we look at it, so from the feed is 100%, and as we increase the density, so more and more goes to floats. And then at the 3 density, we're left with the final 3 sinks. If we look at the lithium, it's on the right-hand side. At the low density, that is our head grade. In this case, the head grade is 1.75, which is quite high for a lithium. And then as you increase the cut density, as the mass decreases, you're concentrating the spodumene crystals, and so the lithium content goes up. And there we've got that effect. If we look at near density, and here we're defining near density as plus or minus 0.05, it relates to the sensitivity of the ore to cut size. So if we're targeting a 2.6 cut density, if we add 0.05 to it, we get 2.65. If we go up at 2.65, we look at the intersection with the recovery or yield curve, we find that's about 60%. If we drop down to 2.55, which is 2.6 minus 0.05, we go up to the yield curve, we find it's 90%. So that difference is 30%. And that's the amount of near gravity if we're targeting a cut density of 2.6. This gray line here is just the results plotted, and you can see that corresponds to that point there. So we've got about 2.6, we've got about 30% near gravity. If we go down to 2.9, we're dropping below 10% near gravity. How do we determine yield and near density for 6% lithium product? So we use our cumulative HLS curve. We start with our 6% lithium, and we go horizontally until it intersects the cumulative lithium grade curve. We then go down to the density axis, and we see that's at a cut density of 2.88. We then look at where that density intersects, firstly, the yield curve or the recovery curve. We go from there horizontally across to the recovery values, and we find that's a yield of about 17.1%. And where it intersects the near density curve, we find that the near density is about 9.9%. So using the cumulative HLS curve, we can predict both the yield and the near density for a given product quality. Nowadays, with the demand for lithium, a lot of mines are now not supplying 6% anymore for spodumene, but 5.5. So what is the effect of reducing the product grade to 5.5? And we can use the same cumulative HLS curve. So what we do is we take 5.5% lithium where it intersects the yield curve. We go down to the cut density. We can see the cut density has dropped. We were at 2.88. We've come down to 2.84. And where does it intersect the yield curve? It intersects it at 22% yield, and the near density increases up to 11.8. So then the relative increase of 28% going from 6 to 5.5. So it's 22% yield over 70% yield. So you can see that reduction, in this case, that reduction in lithium product grade has a significant potential impact on the increase in yield. If we go back to the top size, and we're now trying to establish what our best top size is, as you crush to finer and finer top size, so you generate more and more -1 millimeter. So you can say if you go from 25 to 15 mil, there's a bit of an increase. 15 down to 10, there's more. From 10 to 6.3, there's a lot. And then from 6.3 down to 3.35, there's also a lot more. If we look at the yield based upon the HLS results for the +1 millimeter fractions, then for the top size of 25, that gave a yield of 10%, using the same techniques that we've just shown. The 15 millimeter gave about 17%, the 10 millimeter gave about 18%, 6.3 gave up at 30, and then the 3.35 was about 28. So if you just look at this alone, it almost looks like it's a no-brainer that you've got to use a 6.3 millimeter top size. But what is your overall yield if you do not beneficiate your -1 millimeter? Some plants, they will look at flotation for the recovery of the -1. Other plants will discard the -1. So if we assume zero beneficiation of the -1 millimeter, in other words, it generates zero yield or zero product, then the line reduces from the blue line, which is on the +1, to the orange line, which is the -1 included. And we can see now it's got quite a significant reduction of yield as you go finer, and that's because you've got more and more -1 as you get finer. So if we look here between 15 and 10 millimeters, there's not a lot of increase, and then as you go to 6.3, there's an increase. When you go to 3.35, the overall yield decreases, and that's because you've generated more fines than you're adding yield through liberation. In this case, the top size was chosen at 15 millimeters for practical purposes, because you go to 6.3 millimeters, you need to go for 3-stage or 4-stage crushing, and that circuit also had a recrush stage involved. If we look at our dense medium flow sheet options, and we're going to, in this case, each case, we're going to look at spodumene recovery and petalite. The first one we're going to consider is a single stage. So if you have a single stage process for spodumene, you'll have a target cut density of about 3, and your spodumene reports to sinks. For petalite, you'll have a target cut density of 2.4, and your petalite reports to floats. If we look at 2-stage, for spodumene, we look at 2-stage on the sinks. So what we do is retreat the sinks through a second stage, but both stages at a cut density of 3, and then your final sinks is your spodumene product. If we look at petalite, we'll do 2-stage on the floats. So both stages again at 2.4, and the final floats will be your petalite concentrate. And then if we look at primary and secondary, so if we look at spodumene recovery, what it means, the primary will be about 2.6, and then we will retreat the sinks through the secondary stage at about 3, and the spodumene reports to the sinks. For petalite, we will have the primary also at ±2.6, and then the overflow we'll treat at 2.4, and the final float is your petalite. If we consider these different options, we look at the single stages and applicable to spodumene and petalite, your grade will be okay, but your yield is poor. If we look at the 2-stage, we can achieve a good grade, but the recovery is still poor. And if we look at primary and secondary, which is applicable to both spodumene and petalite, you get a good grade and a good yield. And based upon a lot of test work and a lot of pilot plant test work, the last option, the primary secondary option, appears to be the best one for most lithium hard rock deposits. Now, it's very important to note that particles separate on both density and size in dense medium separation. This is the results of a recent test we did. So it's a single stage. The size range was 6.5 millimeter, and the cut density was 2.4. The sinks is the orange line, the floats is the blue line. So you can see the sinks at about 5% -1, whereas the floats had about 60% -1. And the size effect actually had a major impact then on your grade of the floats, because in this case we were targeting petalite. So you can see there's a massive effect on size. How do we overcome that? Because we need to reduce the size range to increase the efficiency. There's a rule of thumb that your top size to your bottom size ratio should be about 3:1. So if we look at typical size ranges and intermediate sizes, if you're treating a 15:1, 50 millimeter top size, 1 millimeter bottom size, if we choose an intermediate size of 4 millimeters, then the ratio between the top and the intermediate size is 3.75, and the ratio between the intermediate and the bottom is 4. So although we're not achieving that 3:1, we are balancing the ratios between the coarse and the fine. If we look at 10:1 millimeter, top size of 10, bottom size of 1, intermediate size is then 3.35 millimeters. You can see the ratio of the top to intermediate is 3, and the ratio of the intermediate to the bottom is just over 3. And if we look at 6.3:1, where 6.3 is your top size, 1 is your bottom size, you pick an intermediate size of 2.5 millimeters, your ratio of top to intermediate is 2.52, and bottom to intermediate is 2.5, which are both smaller than the 3. So these are strategies that you can use to reduce the effect of size when you're doing dense medium separation. So at this stage, we're ready to start planning pilot plant dense medium separation test work. So if we look at the parameters, Top size, we've got from our liberation test work. The flowsheet option, we've selected the primary secondary because that gives is shown to give the best potential recovery and grade. And size fractions, we use the intermediate size from the rule of thumb. Spodumene pilot testing example. So you have the top size 15 millimeter, bottom size 1, intermediate size 4. Looking at the primary secondary flow sheet, the primary cut densities being evaluated are 2.55, 2.6, and 2.65 because we're looking to maximize the spodumene recovery to sinks. And the secondary cut densities will be 2.9, 2.95, and 3 is to maximize the recovery at product grade. What this leads to is the following test work. So you start with your 15 by 1 millimeter. You separate it at your intermediate size into a 15 by 4 and a 4 by 1. Then you have your primary stage. In both cases, you do a separation of 2.55, 2.6, and 2.65 for both size fractions. And then the secondary on each of the sinks from those primary cut densities, you go and then do a 2.9, a 2.95, and a 3 cut density. So you can see to evaluate all the combinations, there's a significant amount of test work to do. But you need to do this to establish what combination of primary cut density and secondary cut density gives you the optimum or the maximum recovery at yield, at grade. So what about the cyclone? Pilot plant cyclones, typical diameters are between 100 and 250 millimeters and normally use a standard Dutch St. Mines configuration. The operating parameters. So the first one is the operating head, and the operating head is particle size dependent. If you have a coarse top size and coarse particles, you're treating the coarse fraction, a head of 12D is fine. If you've got fine particles, then you need to increase up to 18D. And then for intermediate sizes, you can use 15D. The medium to ore ratio, we're looking at a minimum of 5:1, which is not normally a problem in a pilot plant. We're normally far higher than that. And the cut density comes from the HLS and the test program. So the HLS will give us an idea of theoretically where we should cut. And then for the test program, we will select a range of densities around that. And we measure the cut density using tracers, and an appropriately sized tracer for the size distribution. What about the medium? So if we look at spodumene recovery, the primary cut density is going to be around 2.6. Here we have to use a blend of magnetite and ferrosilicon, whereas for the secondary at a cut density of 3, we can use ferrosilicon. For petalite recovery, the primary will also be around 2.6. We have to use a blend of magnetite and ferrosilicon. And the secondary at 2.4, we have to use a blend of magnetite and ferrosilicon, but it's different to the blend used at 2.6. Why do we use the blends? Because you're trying to manage the differentials within the cyclone. Ferrosilicon is not, in these small cyclones, is unstable at 2.6 cut densities, and that's why we have to add the magnetite to stabilize the ferrosilicon. Here's a test work flow sheet. So we've got our crushed ore, which is 15 by 0. We then screen it into a coarse fraction, 15 by 4, with 4 millimeter being our intermediate size. We generate a 4 by 1 millimeter, and then we have the -1, which we throw away. The 15 by 4 is the coarse that goes through 2 stages, so a coarse primary and a coarse secondary. Both the floats from the primary and the secondary go to reject. The sinks is retreated, and then the sinks from the secondary cyclone is product. And then on the 4 by 1, that's a fine fraction. We have a 2-stage, fine primary and secondary. The floats from both the primary and the secondary go to reject. And then the sinks from the second stage, secondary, reports to product. If we look at the typical mass splits, we start with 100 units. So of the mass, 50% reports to the coarse fraction, the 15 by 4, 30% to the 4 by 1, and then 18% to the -1. If we start with the coarse, so that 51.5, that mass goes to the primary sinks. That will split, in this case, be 20 units to floats and 30 to sinks, and that floats go straight to rejects. The sinks, then, the 30 units goes to the coarse secondary. That splits with 24.7 going to rejects or floats, and then the secondary sinks goes to product. So we generate 6.2 units of product. If we look at the fines, the 4 by 1, that 30 units goes to the fine primary floats. Our fine primary dense medium separation, we have the fine primary floats, which is 21.7, that reports up to rejects. The fine primary sinks goes to the fine secondary sinks. Fine secondary sink floats, reports to reject, and the fine secondary sinks becomes product. If you look here, you'll see just from the width of the lines that although the coarse cyclone had more mass reporting to it, starting with it, both of the coarse and the fine produce similar amounts of product. And the reason is that we get a better yield on the fine cyclone because the spodumene crystals are better liberated. So this is fairly typical that for 100 units of feed, you get between 10 and 15% units of product at grade. Using test work results for plant design. So first important note, the mass splits per size fraction that you generate through the laboratory test work, they are not the same as a full-scale crushing circuit. And you need to benchmark against similar operations to get realistic values. Secondly, the pilot plant dense medium separation occurs under ideal operating conditions in a controlled environment, and you need to derate your yields to account for this. You'll never achieve that in the actual operating plant with everything that's going on. You can compare predicted and actual yields achieved for similar operations. Using test works for plant design, the third thing is mica. And there we have a picture of mica. You can see the mica flat, shiny crystals. Big problem with mica is, although it's got a particle density, the density in the dense medium separation depends on the orientation of the particles, whether they orientate themselves vertical to the flow or horizontal to the flow. They recover preferentially to sinks. So in spite of, even if your cut density in the primary is 2.6, these ones will recover to sinks, and in the secondary as well. If you've got petalite recovery, because petalite focuses on the floats, it'll have a minimal impact. But if you're targeting spodumene, it can have a significant impact of grade. The contamination in terms of your final sinks that the mica gives you, if you've got a lot of mica in the feed. And then the other thing is it can lead to increased medium viscosity, because the mica breaks down and the small particles land up in your medium. If we look at the medium, mica can assist with medium stability, and it can also impact on the medium grade. So you might see that you'd like to use 270D, but because there's mica present, to avoid viscosity problems, you might go to a 150D. If mica is not present or in low amounts, then you'll have to use a magnetite ferrosilicon blend for the primary dense medium separation and for the secondary in petalite. But the secondary dense medium separation for spodumene can be done with ferrosilicon alone. If we look at cyclone diameter, and here we're first going to look at the forces acting on a cyclone. So we have a centrifugal or centripetal force acting in that direction, and a buoyancy and a drag force acting in that direction. If we look at the outward force, we find it's proportional to the diameter cubed, whereas the drag force is proportional to viscosity times just diameter. Because of this, coarse particles will separate efficiently, but fine particles require additional forces. And if we look at the centrifugal acceleration in cyclones as a function of cyclone diameter, what we find is as the cyclone gets smaller, cyclone diameter gets smaller, the centrifugal acceleration increases, and it starts increasing exponentially. The other thing we can do to increase the centrifugal acceleration is increase the operating head. So you can see here that as we increase the operating head, so the centrifugal acceleration increases. Just to give you an idea of a comparative value. So if we're choosing a 420 cyclone operating at 18D, which is a top line, that'll be equivalent to a 200 millimeter cyclone operating at 9D. And remembering in our pilot plant environment, we operating in this region, those size cyclones at those heads. If you've got coarse particles, it's not a problem, because as you said, the coarse particles separate efficiently. But if your lithium is very finely liberated, you've got to be careful about how big you go with your cyclone. In conclusion, dense medium separation of spodumene and petalite is more complex than other commodities such as coal, iron ore, and diamonds. A successful plant design and operation requires, firstly, a well-planned and executed test work program on representative samples. Next, translating test work result into plant design inputs. Thirdly, selecting the correct medium grades and/or blends. And finally, never forgetting about mica. Thank you.